Okay, for this video we're going to use another logistic regression model, and we're going to go back to the e-cigarette datasets one. So you'll want to attach whatever that dataset was called for you. So I've attached it there. Now we're going to try to model e-cig 30-day. That's going to be what we're going to try to model here. Now I've got some previous commands here, and I like to hit up on them and get to where I've got my previous command, and I'm just going to copy this for now. We're going to try to predict e-cig 30 days. Now we could make a factor level variable for year, or I've already got year coded as Y 2018, yes or no. I'm going to look at the rank, freshman or not, and right now it's not a factor level variable. So we need to make that a factor level variable if we're going to use it. So new rank.f, and then it's a factor of new rank. So, and then I've created that new variable there. I think that's the only factor level variable I want to do. Now I have to give this model a name. We'll call it e-cig 30-day model, and then arrow general linear model, GLM, and then what do we got? We're going to go with e-cig 30 days, and then our first variable that we've got will be let's see, I've got we got Y 2018 or something like that. Y 2018 is this one. It's a capital Y, I think. So Y 2018. We could look at potentially whether or not race is an issue. So most of our people were white. There are people that are biracial or multiracial that were coded as 0. So I'll look at that. All right, plus we talked about the rank. Now we created a new one called new rank, right? Plus new rank dot f. That's a factor level variable. We've got a variable called new age right there. All right, so the age of the people. What else? Female, so it's coded as yes, no, so it's already factor level. It's 1, 0. Whether they were in a fraternity or sorority. All right, plus military or not. Okay, do they have smoking parents? Yes or no? One or more smoking parents. So we've got a lot in there. And then we can even see if they've ever used cigarettes in the last 30 days. Smoker 30. Now, it would not be appropriate to ask, have they ever used e-cigarettes, because that particular ever use e-cigarette, you're kind of including the same thing there. Alright, so we've got all this stuff that we just put in this model. Now I'm going to do logistic display on all that stuff for the e-cig 30-day model. And we get a lot of information. If I zoomed out, I could see it more clearly. So I'm going to zoom out so it looks better, so I can read everything. So there's a lot in here in this output. See if I can make it more clear here. All right, let me zoom in. All right, so what are we looking at in this particular model? We're looking at these adjusted odds ratios, or these p-values, these wall test p-values, and you can see that whenever one is included in the middle of this range, this is never significant. And for creating the most parsimonious model, we need to go through and look at which ones have the lowest p-values. Now, on these factor level variables, if any one of those is significant, at whatever the lowest p-value is for that factor level variable, that's what you'll treat the whole group as. So I'll treat this whole group for new rank as 0.585. So we're looking at these factor level variables and seeing which one's the highest, and we do backward selection, and the one that seems to be the highest, that's 508. This is 585. So the new rank freshman, junior, senior is the one that's the least significant. So I would repeat this model and then remove the new rank. So this backward selection process, redisplay it, and then see how it does. And part of the reason why that's not explained or not useful is because we have an age variable in there that probably does better than what rank or school year they're in. So it kind of knocks it out. So this race variable is not significant at 491. And some of that is we don't have necessarily maybe the statistical power. This model randomly or assessed this survey assessed people in our classes, and EKU is just not a very diverse place. So all right, so I went ahead and removed that particular term. So now I'm looking at these wald test p-values again. They're all significant except now the military variable is not significant. So I'll go ahead and get rid of that one and then redisplay it and then make sure that they're all significant now. Now this smoking parents one is marginal. So it's 0.05. So, the range is 1.00 to 2.12. So, might keep it. I'll probably keep that one. It's right on the fence. So we'll go ahead and keep that one. And overall, there you see all these terms, and you can look at them and see, okay, people in 2018 holding all these other factors constant were 3.3 times more likely to use e-cigarettes. Age, for every 1 year older you get, there was an 11% reduction in the use of e-cigarettes. By being female, there was a 1 minus 0.57, there was a 43% reduction in e-cigarette use. Guys, or not just guys, but guys and girls in fraternities or sororities had a 2.98 times greater odds of e-cigarette use. Having smoking parents increased the odds 1.46 times, or 46% greater than 1. So having smoking parents increased the odds. And then look at this huge odds ratio. If you were a smoker in the last 30 days, your likelihood of using e-cigarettes were 15.79 times greater. The odds of e-cigarette use was 15.79 times greater among smokers than non-smokers. If you were to do 15.79 minus 1.0, you're going to get like, this is just a huge, percentage. It's not like 157. This is, just an insane, it's a lot higher than that. So, all right, now, how effective is this model at predicting recent e-cigarette use? And these are also all potential risk factors, or this is a protective factor here by being female. Being older is actually probably protective here as your age goes up for e-cigarette use. How does it perform with our area under the ROC curve? Area under the ROC curve, this is our e-cig 30-day model, and we get a much more robust area under the ROC curve table. So it's a large table, and there's the area under the ROC curve, 0.81. So if we were to go back and look at that particular website, this article that's quoting some statements from Stan Lemashaw's Applied Logistic Regression book, you see 0.8 to 0.9 is excellent discrimination. Excellent discrimination. All right, so that's a little bit on this. Now, ordinarily, we would also look at doing a goodness of fit test, but it's not, our goodness of fit test does not work in this particular, somewhere way back here, I've done one once before, logit goodness of fit, for trying to predict this. But we'll get an error. We're going to get an error when we try to use this command. That's the command for logit goodness of fit test, the Lemmashaw, Hosmer-Lemmashaw goodness of fit test. it probably will not work correctly. And I need to add a parenthesis there. And the reason why is because we've got a lot of missing data in here. And this particular RStudio with that command, it only works when all the missing values for everything used are totally removed. So you would have to go in there and delete every single missing value for everything that's in this model in order for that to run. I've already done that with another data set, and it runs. And in that goodness of fit test, you want high p-values. You want no significant difference between your true e-cigarette 30-day data and your model predicted one. So it runs a chi-square test comparing your actual e-cigarette use in the last 30 days versus what your model predicts. So we would use that type of command. I'm not going to have you guys do it for this class, but if we were teaching applied logistic regression, we'd make a big deal about it. We'd also be looking at outliers and doing model diagnostics and tolerance and collinearity assessment, that kind of stuff. Again, RStudio isn't as good right now at doing those things as SAS and Stata. So one last thing that we're going to do, I'll do it in the, I'll go ahead and show you in this video, is if you were to do summary on your model, like you did on linear regression, but if we were to do summary on this e-cig model, here we go, you're going to get something like this. And it still shows you whether or not your model terms are significant. And since we've got the most parsimonious model, everything is significant here. And these would match up well. You see, these match up exactly with that logit display. Those p-values are just fine. The estimates here are our model coefficients, our beta values. And you see some that are positive and negative. Don't interpret these as positive or negative all the time. You know, it's what you need to do, what the other command, logit display or logistic display, does is it converts those for us. For example, if we had this particular one, we'll go to Greek. I'm going to copy that number right there. What's the odds ratio for that? Well, it all comes from a formula. So logistic regression has these formulas where we're dealing with e to the this plus the e to the, you know, it's a complicated formula to a person who doesn't use it a lot. So if we were to do e to the 1.09258 for Greek, we get 2.98. So the exponentiated beta, the exponentiated coefficient here, is our odds ratio. So Greek, it's right there. It's 3.0 according to this because it rounded 2.98 to 3.0. If we were to exponentiate something else, you know, we've got right there smoking parents, 0.37. I'm going to go over here, I'm going to exponentiate it. When I do that, I end up getting 1.457. 1.457. So I scroll up, I look at my model for smoking parents, and it says here 1.46. So I had 1.457. So in the event that you ever have to make a table for a scientific paper, you will sometimes see beta for the coefficients, and then you may then see standard error of beta, and then you may also see crude odds ratio, COR, and then adjusted odds ratio. From an epidemiologist perspective, we like seeing the adjusted odds ratios and the crude to a certain degree, because those are more helpful for us in communicating those statistics. So very similar approach to linear regression with regards to creating the best possible model. But this only works when our outcome variables, in this case, are categorical, and especially in this case, this is binary logistic regression, predicting a yes-no outcome. So you'll do an example for your homework on this particular topic, and I think you'll find it easier than you may have thought going into this. So that's all for this section, and I wish you the best.